Lab 7, adding a 7-segment display driver. In the final alarm clock design, we display time on a 7-segment LCD display, and hence the 4-bit output of the previous lab, which indicates a single digit of the time, is to be encoded into its 7-bit equivalent in order to drive a 7-segment display. We will use a combinational process to implement this. We also illustrate in this lab to visualize the output graphically. We will create a new design called DDRV. This will have the same basic function as a multiplexer design of the previous lab, except that the output disp_7seg is now 7 bits wide to drive a 7-segment display rather than the 4-bit output display to represent the value in binary. The combinational process encodes the 4-bit display digit into its 7-bit equivalent. For display values which do not represent a decimal digit, for example 1111, an error should be shown on the 7-segment display.
We will be using a 7-segment LCD display for each digit of the alarm clock. The input to the display is a 7-bit vector, that is disp_7seg, where each bit represents one segment in the display. If the bit is 1, then the associated segment with this bit is lit. The diagram shows to which bit each of the segment is associated with. Say for example, to represent 2, we should drive high on all the bits except for bit 5 and bit 2. Similarly, to display E, we need to drive high on all the segments except for segment 1 and segment 2, that is bit 1 and bit 2. Note, binary values 1010 to 1111 cannot be represented on the 7-segment display. For all these, as well as any unknown value such as UUUU, we will indicate an error condition by outputting the encoding to display as E. The encoding for the 7-segment display is defined for you in a package named alarm_types in the file p_alarm_types.bht. The bit patterns for each of the digit is declared as constants for better readability. In the design file, we can use constant names instead of the bit patterns by importing the alarm types package. Also, so far we have verified our code by examining the design waveform during the simulation. It would be better if we could view a graphical representation of our display to verify that the correct segments of the 7-segment display are being lit. This is known as visualization. In this lab, we will use a technique for viewing the disp_7seg output in a specially written visualization tool. VHDL can write the value of any signal to an external file format which can be displayed in a graphical window, such as the one shown on the right. A VHDL procedure called disp1 is applied to perform this operation. This functionality allows us to verify our design using a graphical representation of disp_7seg rather than examining the bit patterns in a waveform viewer. The disp1 procedure is defined for you in a package named p_disp1 in the file p_disp1.vht. Let us code, simulate and synthesize this design. The 7-segment encodings for each digit are declared as constant in the alarm_types package in the file p_alarm_types.vht. Compile this file by running the extrude command along with the compile option. Copy the design file mux3.vht to a new file named ddrv.vht and rename the entity to ddrv, remembering also to change the entity name referenced in the architecture. Add a use statement before the ddrv entity to make the contents of alarm_types package visible to your design. The 4-bit output display is replaced with 7-bit disp_7seg output, and the 4-bit display becomes internal signal here. Add a combinational process to convert the 4-bit display digit into its equivalent 7-segment encoding. The key statement is the easiest construct to use, and hence we use this to implement this encoding logic. We see that when display is 0000, output is assigned with 0-digit encoding. When display is 0001, output is assigned with digit 1 encoding, and so on. For all other values from 1010 to 1111, the output is assigned with error segment encoding. Compile this file by executing the exrun command along with the compile option. Copy the testbench file t_mux3.vht to a new file named t_ddrv.vht and rename the testbench entity to t_ddrv. Update the component declaration and instantiation to match the DDRV design. Add this use clause to enable the use of type conversion functions. The initial process stimulus remains the same. We add an extra for loop to apply a full binary sequence to a testbench signal time_data at intervals of 10 nanoseconds. Add the visualization procedure disp1 using the following concurrent statement. This procedure writes out the digit represented by disp_7seg onto clock.txt file to display the output graphically. Compile this file to check for any syntax errors. Let us simulate the design. The testbench will create a file called clock.txt containing a character representing the 7-segment display. View the clock.txt file in an editor. You may need to keep refreshing the file to see the changes in the output. Run the simulation in short steps so each output value can be observed in the 7-segment display. Right-click on the top file and select on Send to Waveform window from the drop-down menu. Let us add the signal display from the RTL to ease our analysis. Let us run the simulation in small steps by clicking on the Simulation tab and selecting Set Breakpoint Time from the drop-down menu. Set the simulation breakpoint interval to 10 nanoseconds. Run the simulation by clicking on the play icon. Adjust the time scale and the zoom options to view the output conveniently. We see the simulation is at 10 nanoseconds now. Press the play icon again and adjust the scale. The simulation time is 20 nanoseconds now. Step forward by pressing on the play icon every time. We can view the output graphically by viewing the contents of clock.txt file in an editor. We see at 100 nanoseconds value of display is 0 and hence digit 0 is written onto the file clock.txt. Run the simulation again. At 120 nanoseconds, the display value is 2 and hence digit 2 is written onto clock.txt. Step forward and see at 130 nanoseconds, display value is 3 and hence digit 3 is written onto clock.txt.
We can also run the test in the batch mode and observe all the output just by writing onto the file in the append mode. Change the write mode of the file to append mode. Now let us run the simulation in batch mode. Let us view the output in the clock.txt file. We can view the output in the file clock.txt file. In the test bench, we see that by keeping show underscore t high, we loop through all the time data values. Hence, in file clock.txt, we see the values increment from 0 to 9. For binary values 1010 to 1111, it should output an error condition. We see it happen, but there is an issue with the 7-bit encoding for the error signal. Let us fix this and rerun the simulation. Let us go to file p underscore alarm types.vht. We see that the error encoding for E is 7C, which actually has to be 79. Let us fix this and rerun the simulation. Let us view the contents of clock.txt file. We see the value E being displayed properly. Let us synthesize this design. Create a genus shell trickle script to execute the genus commands.
Change the design variable to ddrv. Read the files p underscore alarm underscore types.vht and p underscore disp1.vht along with the design file. Invoke the genus tool by executing the genus command. View the schematic in the schematic pane. You can observe the synthesized output. This completes this lab.